Assalamualaikum and greetings to all, especially my lecturer Dr. Wan Salha. Here, I would like to present an analysis of study entitled A Mixed Activity-Based Costing and Resource Constraint Optimal Decision Model for IoT-oriented Intelligent Building Management System Portfolio. Before we go further, my name is Marni Azira binti Markom and currently I am a student of MBA of Engineering Management Program in UC Malaysia Perlis. Back to the study. This study was conducted by Chin Hao Yang, Quen Chang Li and Xin En Li from National Defense University of Taiwan and Soochow University of Taiwan. This paper was published in Sustainable City and Society Journal in year of 2020. Okay, next, for this presentation, I would like to highlight the content involving introduction, literature review, methodology, result and discussion, contribution and conclusion, and last but not least, the proposal on future works. For introduction, there will be 3 topics, which are highlighted issue, problem statement, and objective. For this study, United Nations report that 66% of the world population is expected to live in urban area by 2050. Government will face challenge to supply basic resource while ensuring overall economic, social and environmental sustainability. The European Commission suggests that smart cities are required and necessary, as smart cities can provide long-term economic growth and well-being of citizens to obligate and control climate change. 2 essential components in smart city have been initiated. First, intelligent building and intelligent system. It is stated that intelligent system is used to support monitoring and maintenance. Also, it is considered as a solution to overcoming derivative problems such as pollution, poor sustainability, and weak security. For intelligent building, it is divided into 2 categories for evaluation. First, intelligent office building and smart factory. From here, 2 main problems were considered and authors believe that they can find the solution by conducting this study. The first problem is the formulations of IoT-oriented IBMS strategic plan is complex. And then, second, the cost planning evaluation of sustainable city development is critically important. Then, based on the problem statement, they initiate objective of this study. As generally, the objective is to develop an integrated decision model to be used in acquiring optimal IBMS portfolio through the method A&P, ABC, and ZOGP method without sacrificing profit margin, while ensuring sustainability energy development. In order to ensure this main objective is achieved, they initiate 2 sub-objectives. First, to find the key determinants that provide an optimal portfolio of IoT-oriented intelligent building management system, IBMS, adoptive strategy for decision makers, and then to propose an IoT-oriented decision-making model with a critical perspective and criteria for the assessment and determination of management system for the intelligent building. Next is literature review. In literature review, it discusses on IoT technology and IBMS characteristic and present an integrated decision model that incorporated key evaluating criteria and ABC concept. The first discussion is on IoT. Second is evaluation criteria for IBMS, and the third discussion is on IBMS cost assessment using ABC method. For IoT or Internet of Things, IoT is essential component for IBMS. It is a controller network based on intelligent microprocessor and aims to be comprehensively supervise, control and optimize a building operation system and service, such as ventilation and lighting. It is considered as a type of open platform that combine individual pieces of building equipment into a single integrated database. For evaluation criteria of IBMS, the criteria are derived from the literature review. Ultimately, the evaluation criteria for IoT-oriented IBMS are consist of four main perspectives, which is smart technology development, market development potential, socio-economic benefit, and regulatory environment support. Based on four perspectives, 12 criteria are created to assess the IBMS. So this is the 12 criteria that created based on each of perspective. Next is the IBMS cost assessment using ABC method. ABC method generally is a cost accounting system. The literature specify that ABC is widely used to analyze review decision issues, particularly for environment and energy issues such as public transport project. In this study, ABC is used as cost object. This figure shows the ABC flow of the IoT-oriented IBMS. ABC used two-stage procedure to assign resource cost, here, to cost object. Generally, ABC divide IBMS cost into two categories, which is consists of direct cost and indirect cost. Direct costs include material and labor costs, while indirect costs include energy consumption and environmental. So between resource and cost object, there is the activities in the IBMS assessment. Next, for methodology, there are two stages of work, which are mixed multi-criteria decision-making (MCDM) approach and an empirical example for IBMS strategy. In work of mixed MCDM approach, it illustrates an evaluation model procedure that not only construct a network structure for IBMS, but also find an optimal portfolio for IBMS, and it's still allowing for limited internal resource. The procedure for mixed MCDM is a hybrid model approach that consists of DMetal, ANP, and ZOGP. DMetal is a structural modeling tool that used to solve complex relations. This technique has been applied to many decision-making issues, including merger and acquisition interaction network relationship. In this work, an average direct relation metric is constructed and calculated. Then, it follows with the calculation of the normalized direct relation metric and total relation metric. For ANP works, analytic network process. It is a method to solve multi-objective decision. It has been widely used in academic field, including urban renewal in southern India and green roof type selection study. In this work, a network structure is set up and the priority of criteria is calculated. Then, criteria in the whole system are compared to form a priority weight metric and conduct the consistency test. The large approach in hybrid model of MCDM is ZOGP. It is a practical tool for handling multiple objectives as well as single objective problem and for acquiring the objective of an organization while considering limited resources. However, The aim of ZOGP method does not to optimize the objective directly. Instead, its attempt to minimize the derivation between the desired goal and the realized result so as to provide suggestion to decision maker for resource allocation. Next is a work on empirical example for IBMS strategy. There are two stages of work here. First is empirical example assumption, and second is application of the integrated method. For empirical example assumption, it is divided into two categories, which are intelligent building and smart factory. For each category, four alternatives for decision hierarchy are formed based on the formulated criteria and A&P procedure. For intelligent building, alternative 1 is CLS, Comfortable Living System. CLS is mainly to create a comfortable environment for workers through the monitoring of air quality, noise pollution, lighting, and thermal. Alternative 2, Disaster Prevention System, DPS, is an emergency situation such as fire hazard or earthquake. DPS is capable of instantly identifying the safest route for evacuation. Alternative 3, Equipment Maintenance System, EQM. EQM can monitor all equipment in the building and clearly show any operational error. It improves the efficiency of maintenance staff and enhances the smooth operation of the facility in short order. Alternative 4, Energy Management System, E&M. Optimize energy supply and consumption to reduce carbon dioxide emission and the office building operational costs. For smart factory, alternative 1 is machine monitoring and predictive maintenance, MPM. MPM is used to constantly monitor essential production line equipment and production status. Data are recorded and transferred in real time to the cloud for predictive maintenance analysis, which increase productivity and reduce maintenance costs. Alternative 2, Manufacturing Execution System, MES. It collects dynamic production process information, optimizes production allocation, achieves advanced manufacturing, and traces the production process of product. The production process information can be monitored remotely. Alternative 3, Factory Environment Monitoring, FEV. With FEV, the factory safety can be monitored for dust, gas, carbon dioxide, water, and other hazardous material in order to optimize factory operation and ensure the quality of the factory environment. FEV also specializes in the inventory monitoring of high-risk storage. Alternative 4, Factory Energy Monitoring, FEE. It provides the optimization of energy supply and consumption to reduce carbon dioxide emission and factory operation costs. The final work is application of integrated method. This work here have four stages of work. It starts with evaluate relationship among perspective and criteria with the mentor. Next is priority weight of evaluation alternative created by A&P. And the third stage, direct cost and allocation of indirect costs according to ABC for IBMS. And then last but not least, optimal portfolio for IBMS using the 0-1 goal programming model. At the end of the work, the integrated MCDM model can fully utilize the available resource of the organization and also determine an optimal investment portfolio for implementing IoT-oriented IBMS strategies. Next, result and discussion. As stated in methodology, there are 5 main steps to create a decision-making model for IBMS optimal practice. In this section, only 3 results that found from the 5 main steps are shown. The first result is a priority weight using A&P. Here, ANP has success to compute the weight for each alternative and priority rank also are given. For intelligent building, the first rank is a DPS, which is disaster prevention system. And then the second is a EQM, which is equipment management system. Third is a ENM, energy management system. And the fourth priority is CLS, comfortable living system. For smart factory, the first priority is FEE, which is a factory energy management. And then the second priority is MPM, which is machine monitoring and predictive maintenance. And then the third priority is FBV, is a factory environment monitoring. And the fourth priority is a manufacturing execution system. The next highlighted result is a resource requirement and essential limitation of the IBMS. For intelligent building, there is a resources requirement including budget installation cost, consultation fee, target saving energy percentage, IoT infrastructure cost, and implementation period. Here, it shows that EQM has the highest cost, which is in total is 3,515 times 10,000. Compared to DPS, which is actually DPS is the first priority in intelligent building. Next, for the highlighted result of resource requirement and essential limitation of IBMS for smart factory. The resource requirement is similar with the intelligent building, but here for alternate uh, the highest cost for is a for alternative MES, which is a manufacturing execution system, which is the budget installation cost is 2,435 times 10,000 unit price. And then here, FBV has a highest implementation period, which is a 14th month. For discussion, according to the DR value by the Demeter method, this study found that the major influencing perspectives are smart technology development (STD) and market development (MDD) for IBMS selection. The criteria of the cost group include technical practically, technical reliability, user acceptance and perceived usefulness, as well as industry market competitive, ecosystem value chain, user privacy, security, and etc. Based on this evaluation criteria for IBMS, government subsidy policy (GSP) ranked first under the cost group. This shows that government policy is the driver of IoT-oriented IBMS development. Also, the interrelation of act and regulation with other criteria shows government policy to be a catalyst for IoT-oriented application deployment. The cost evaluation of ABC and other relevant constraints are viewed and resource constraints within the decision-making process. Most importantly, the cost planning evaluation of sustainable city development is critical. The study incorporated the LCA concept and identified life phase activity requirement as applied to an intelligent building management system. The cost planning process also provides information about resource capacity and core activities and then evaluate cost improvement opportunities. The result indicate that disaster prevention system and energy management system would be selected for the office building and factory environment monitoring FEV and factory energy monitoring FEE for the smart factory through the integrated decision model. As contribution and conclusion, General contribution here is this study has provided a new decision model integrating activity-based costing and resource constraint into IBMS optimal portfolio selection. This contribution can go to three types of agency. First, academia. This study established a hybrid decision model incorporating cost measurement into the resource constraint content and apply a mathematical planning decision model for IoT-oriented IBMS portfolio. And then for industry agency, this model can help decision maker accurately understand how to allocate resource and improve inefficient resource input in each activity via appropriate cost driver. And for policymaker, the optimal IBMS selection model as proposed takes into consideration cost assessment solution and limited resource. And for conclusion, the proposed method can solve problems having multiple criteria, interdependence and resource constraint. The outcome of this study should be useful for IoT-oriented IBMS strategy implementation. Next, proposal on future work. In my point of view, this study can be expanded by testing the model in order to get the effectiveness performance. Many agencies and companies should be taken place to involve in this study. That's all from me. Thank you.